Cell stoichiometry is much like any other kind of stoichiometry. The difference is, one, the units involved, and two, how you're going to get your reaction. The nicest thing about this stoichiometry is the reaction part. There's no balancing involved because it is just simply a single half reaction. And we'll see what I mean by that just in a minute. Other than that, it's the same. So how are you going to know? Well, like I said, the units are different. Moles as they're normal. New current, you'll see current typically given to you in amps. Well, 1 amp isn't going to be useful. An amp isn't very useful, but you can convert that directly into a coulomb per second. So 1 amp is 1 coulomb per second. What's a coulomb? Well, a coulomb represents charge on electrons. And it says here your time must be in seconds. Then you have this new conversion factor, this Faraday's constant. It's in your data booklets, you don't have to memorize, but please make note that it's coulombs per mole of electrons. Okay, so that's a little bit new. Okay, and also this exponent here on the base 10 is a positive 4, not negative. So what will the question look like? We've decided to produce a ton of chlorine gas. We want to know how long it's going to take to do this using a current of 150 amps through a solution of sodium chloride. Well, as I mentioned, you'll need a half reaction. So even though we have sodium around, even though we have water around because it's aqueous, I don't care about those things because it's just the chlorine gas being produced that we're concerned with. So as a result, I just use this half reaction. So next step, there my reaction is, I have it, it's balanced, good to go. Next thing, let's write down the information we know. I was given 1 ton of chlorine gas, but that's not very handy, so I converted that into 1 megagram. You could have also converted it into 1,000 kilograms or 1,000,000 grams, whatever you like. I just use megagrams because it's a little more convenient as far as neatness goes, I suppose, and significant digits. So I have 1 megagram of chlorine gas. Then I have the current of 150 amps. I'm looking for the time it takes. And then I have my Faraday's constant. All of those types of things, anything to do with current, charge, time, all those things go under electrons. Okay, this is where the big difference is. You have electrons as part of your reaction, and you're going to treat them just like any other element or compound in any other type of stoichiometry. So please, please, please make sure you use them as such. So what do we do after we have everything written out? Normal stoichiometry starts. First step, let's find the moles of our known substance. So that's what I've done here. I've converted the megagram into moles of chlorine gas just using my molar mass. Okay, watch, it's Cl2, so the molar mass was doubled. Then next step, once you find the moles of your known, you're going to find the moles of your unknown using your mole ratio. And again, as you can see here, I've got 2 to 1, but the 2 is for moles of electrons. Okay, there's a formula in your book that you'll see. It can be very helpful, but often those who use it kind of forget to utilize the mole ratio. Then after that, once you have your moles of your unknown, then you solve. In this case, I have a little bit of extra converting to do because I have Faraday's constant as well as current to deal with. The Faraday's constant will always allow us to convert back and forth between moles of electrons and coulombs. So I'm going to use that to cancel out my moles of electrons from the previous step. And then I need to get rid of the coulombs, and my current will allow me to do that. Coulombs then cancel out. And then from there, I took an extra step to convert it into hours. You wouldn't have had to. You could have left it in seconds if you like. Just watch your significant digits in the end. All right.